Yes, this is Carl Perez again, Math 111, Section 5.9 in our text. Today we're going to talk about solving equations by factoring. Well, let's take a look back at where we've been. Let's say in Chapter 2, as you might recall, we were asked to solve equations that more or less look something like this. 2x minus 3 equals 8. And of course we could solve this by doing algebra type things to both sides of the equation, namely either adding, subtracting, multiplying, and dividing. The goal being to isolate x on one side of the equation, of course get a number on the other, thus solving the equation. Of course here we would add 3 to both sides, get 2x equals 11, and then dividing both sides by 2, I get x equals 11 halves. Alright, not a big deal, and that's ancient history now. Let's say in Chapter 5, in particular in Section 5.9, we're going to ask you to solve something like this. 2x squared minus 3x equals 8. A somewhat similar looking thing to the first example we gave you on the left, but we've got some trouble. If we try to add or subtract or multiply or divide both sides of the equation by whatever elements we choose, we can't isolate x on one side of the equation because x squared and x are unlike terms. X squared is a degree 2 term and 3x is a degree 1 term. So no matter how hard we try, we can't combine them, hence we can't isolate x on one side of the equation. Alright, so what do we do in this type of situation? We still need to solve this higher degree equation, right? And what we're going to do is use a convenient little trick which will enable us to find solutions by factoring. Let me give you an example of what I'm talking about. Suppose I ask you to solve something like this. X squared plus 5x plus 6 equals 0. Alright, we've got kind of a standard looking degree 2 trinomial equal to 0. Well, there are values of x that will solve this equation. Our goal is to find them. Notice, I'll call this a polynomial equation. Of degree 2. And for obvious reasons, the highest exponent you see on that polynomial is 2. So I'll call this a degree 2 equation. All right, what I can do is, once I've got this equation in what we call standard form, in other words, terms are arranged in decreasing degree, I'm going to see if I can factor this, and if you'll notice, this left-hand side of the equation does indeed factor into x plus 3 times x plus 2. And of course, then that product equals 0. It's important to note that this factored form is now a product of two binomials equaling 0. Now we can go farther. I'm going to use what the book calls a zero product rule. That's a fancy way of saying this. If you know that two things multiplied equals 0, that means one of two things, either A equals 0 or B equals 0. That's what we call our zero product rule. A product of factors equals 0 means that one or the other factor equals 0. So what I can do is use this zero product rule in this situation. In other words, branch this product equation into two other simpler equations. Well, of course, we can solve these very easily. So now x equals minus 3 or x equals negative 2 are our two solutions for x. So notice what's happened here. We've started out with a degree 2 equation, Through factoring, we've branched this out to two simpler degree 1 equations, which we can solve as in Chapter 2. Alright. This use of factoring is by far the most important use of the factoring process. Notice in Chapter 5, we spent a lot of time factoring. GCF factoring, trinomial factoring, difference of squares factoring, other types of factoring as well. In Chapter 5, the most time was spent on factoring. Learning how to factor different types of expressions with different types of factors. And in section 5.9, we will reveal the most important use of factoring, and that is to solve equations. Now notice, in Chapter 2 we could solve equations, but only degree 1 equations. In 5.9 we're going to solve equations of higher degree. How high? Well, higher than 1. 2 or higher. Another example. Let's say we want to solve 3x squared equals 6x. Now this is not so quietly arranged, not quite so nicely arranged as our previous example. 3x squared equals 6x. Well, pretty much in all these problems you'll want to arrange things in standard form. In other words, arrange your terms typically on the left-hand side in decreasing degree, going left to right. So let me write that down. Usually it's a good first step to convert your equation into standard form. Well, terms are arranged on the left, typically, in decreasing degree. So here we end up on the left with a degree 2 term minus a degree 1 term equals a constant or a degree 0 term. Alright, let's look to factor this. 3x squared minus 6x. Of course I can factor it. Well, it's not a trinomial factoring. We're not going to unfoil this. There's a GCF of 3x we can take out, using working our distributive law in reverse. So I end up with 3x times x minus 2 equals 0. Just to make things a little more clear, I'm going to isolate that 3x factor in parentheses, because now I'm going to apply my 0 product rule. Alright, my degree 2 equation will then branch off to two simpler degree 1 equations. Oh, it's important to put an OR statement because one or the other solution will work here. So if 3x equals 0, of course if I divide both sides by 0, 0 over anything equals 0, so I get a solution of x equals 0, or with the right branch x minus 2 equals 0 means x equals positive 2. So we started out with a degree 2 equation, and we end up with two solutions, x equals 0 or x equals 2. Okay, let's try another one. Solve 9x squared equals 25. Alright, how are we going to solve something like this? Well, again, in wide strokes, we see a degree 2 equation. We'll probably want to get it in standard form and try to factor it. That's the only tools we have right now to solve equations of higher degree. So, arranging terms in decreasing degree, I'll subtract 25 from the left-hand side, or from both sides. Alright, so I will have a 9x squared minus 25 on the left and equals 0 on the right. Of course, we'll recognize this as a difference of squares. On the left, I can then factor it instantly as 3x plus 5 times 3x minus 5. And I'll then have that product equaling 0. And if a product equals 0 by our 0 product rule, well, that means one or the other factor equals 0. And I'll work on the left-hand branch first. I'll subtract 5 from each side and then divide by 3. So on the left branch, I'll have a solution of x equals minus 5/3. And on the right branch, similarly, I'll add 5 to both sides here and divide by 3, resulting in the solution x equals 5/3. So again, I'm starting out with the degree 2 equation. By factoring and applying my zero product rule, I break that down into 2 degree 1 equations, 2 simpler degree 1 equations, which then I can solve very easily by adding or subtracting, multiplying or dividing both sides to isolate x in one or the other branch. Okay? Another example. And these get a little nastier, but the idea is the same in all of them, really. To solve equations of higher degree. Alright, problems like this one tend to panic students on test days, so listen up out there. X equals 6/5 minus 6/5 x squared. This is a degree 2 equation because the highest exponent I see on any of my variables is 2, so degree 2 equation. I should be able to solve this by factoring. Well, you got to get it in standard form first. And the first thing I would do here is to multiply both sides by 5. All terms, both sides, to get rid of these fractions. Alright, so on the left-hand side, I'll end up with 5x. Well, you've got to apply your distributive law on the right-hand side. 5 times 6/5 is just 6. The 5's cross-cancel. And 5 times 6 minus 6/5 x squared is going to be minus 6x squared. Looks much better already. Let me erase the guidelines here. Now I'll want to arrange my terms on the left in decreasing degree. Well, I'll add 6x squared to both sides. 5x is already on the left, and then I'll subtract 6 from both sides. So I get this resulting trinomial equation in standard form. 6x squared plus 5x minus 6. I think I can factor this. I'll have 3x and 2x in the first slots, and I think a 3 and a 2 in those last slots as indicated. If I have an outer product of 9x and an inner product of 4x, I can get those two to add up to a positive 5x if I play the signs right. So let me do that. So get a minus 4x for my inner product and a plus 9x for my outer product. And indeed, that will do it. Okay. I will then branch this off into 2 degree 1 equations. And if you feel comfortable skipping steps after you've done a few dozen of these, I suppose you might want to not write down every possible step. I'll get 3x minus 2 equals 0, or 2x plus 3 equals 0. So I get 3x equals 2, or x equals 2/3 on the left branch. And if 2x plus 3 equals 0, that means 2x equals minus 3, or x equals minus 3/2 on the right branch. And don't forget to put that or word in between them. It means these are both solutions to this given degree 2 equation. Okay. Another example. Alright, some of these get a little nasty, but again the idea is the same. Here's one of that type. I get 3x plus 1 squared equals 6 times 3x minus 1 plus 3. Alright, the real battle here is going to be to get it in standard form. Well, clearly you've got to perform some operations. I've got to square this binomial, I've got to multiply this binomial through by 6, and then I've got to combine like terms to get things in standard form. So let's take care of business here, one side at a time, I guess. I'm going to square 3x plus 1 here on the left-hand side. Well, that will give me 9x squared plus 6x plus 1. Remember, you're squaring a binomial, so you've got inner and outer products to express also. On the right, 6 times 3x is 18x, minus 6 times 1 is 6, plus 3. And if I get things in standard form, let's say, oops, yeah, no, that's right, I mean, that looks right. There is no other x squared term, so 9x squared is going to stand alone. If I subtract 18x from both sides, well, 6x minus 18x gives me a minus 12x on the left. Minus 6 plus 3 is minus 3, and then I'll add 3 to both sides to get 4 on the left and 0 on the right. So basically I subtract 18x from both sides, and I'll add 3 to both sides to get this resulting trinomial of degree 2. Alright, looks like this factors on the left. And if I pick 3x for my first slots and 2's for my last slots, let me check. The first product is 9x squared. The inner and outer products are both minus 6x, and those indeed add up to a minus 12x. And the last product, minus 2 times minus 2, is plus 4. So indeed, I have written down correctly the factored form of the left-hand side. And you probably noticed something. I won't tell you what it is right away. If I then branch off to 2 different degree 1 equations, I'll get 2 solutions, x equals 2/3 or x equals 2/3. Now you may have noticed that these binomial factors are both the same. 3x minus 2 times 3x minus 2. And when that happens, of course, you're going to have a duplicated solution. Depending on what book you read, some books call this repeated solution. I think our book calls it a repeated solution. Sometimes you'll call it a double solution. Some books call it a double root, repeated root, whatever. Our book calls this a repeated solution of x equals 2/3. Okay? Alright, and that can happen sometimes. You don't always have 2 unique solutions to degree 2 equations. You could have 2, you could have 1. Some equations can't be solved and you have no solutions. Depends on the equation. Let's go to another screen here. Here's another higher degree equation. Alright, well, this is a degree 3 equation. Up to now we've only had degree 2 equations, but again, factoring can be used to solve higher degree equations, degrees higher than 1. Let's try and get this in standard form and see what happens. Well, not very hard to get this one in standard form. All you need to do is subtract 2x from both sides. Alright, and I'll notice, before I try to factor this as a trinomial, there's a GCF here. And what's the GCF? Well, of course, it's x. X can be factored out from that trinomial. So I have the resultant expression x times 6x squared minus x minus 2. What I'm going to do now is try to factor this trinomial in parentheses as a product of 2 binomials, and I think I can do it in this fashion. Let me check it quickly. 6x squared is the first product. 6x squared is the first product, 3x is the outer product, minus 4x is the inner product, and those indeed add up to a minus x, and the last product is minus 2. Alright, so I'll play the same game with the zero product rule, just to make things very clear that x, don't forget about that x. Right, that x is a factor of that trinomial, so I have to put it in the list. So basically I'm going to branch off to 3 equations with my zero product rule. Either x equals 0 from this factor, or 3x minus 2 equals 0 from that middle factor, or 2x plus 1 equals 0 from that third factor. And of course all these can be solved very easily now. So x equals 0, well, that branch is already solved, or x equals positive 2 over 3, or x equals 2/3, or 2x equals minus 1, and then x equals minus 1 over 2 as a solution to that third branch. So here, notice I've got 3 solutions. Don't forget about x equals 0. Let me make that a little clearer over here. X equals 0. 0 is a number. It lives on the number line, and it is a solution to our given equation. Okay? So here I started out with a degree 3 equation, and using some manipulation and our zero product rule, we can reduce that to 3 degree 1 equations and end up with 3 solutions. Alright, one more before we call it a day here. This is in your homework list. I believe this is number 81 on page 499 in section 5.9. Solve the following equation. N times 3n minus 4 equals n minus 6 squared plus 11n minus 1. Alright, again I've got some manipulations, some operations to perform before I can free up my like terms to combine in order to get things in standard form. Well, so typically, well, on the left hand side I've got to perform this product. I've also got to square n minus 6, and once I free up those parentheses I can then put like terms together and get things in standard form. Let me start out on the left hand side. I'll get 3n squared minus 4n on the left. On the right hand side, if I square n minus 6, I'll get n squared minus 12n plus 6 squaring that binomial, and I'll need to add that to 11n and then subtract 1. Oops, made a mistake. Anybody catch it out there? I'll tell you what, since it's maybe a common mistake, since I already made it myself, let me go into a little more detail here. Beware of that squaring this binomial here. Often gives problems, so maybe it's good that that happened. Let me try it again. To make things ultra clear, let me rewrite this. N minus 6 squared is indeed n minus 6 times itself. No, it's not n squared minus 6 squared. And then it should be a plus 11n plus 11n minus 1. Alright, let me go ahead and perform the indicated operations now on the left hand side. I'll get 3n squared minus 4n on the left. On the right, foiling these two binomials, I'll get n squared minus 6n minus 6n will add up to a minus 12n, and multiplying the last products I'll get a plus 36. I wrote down 6 last time. It's a positive 36 there, so please note that. Plus 11n minus 1. Alright, I think the worst is over. Now I'm going to combine like terms. If I suppose if I crunch things together on the left-hand side, it may make my life a little easier. So on the left-hand side, I'll see a minus 12n plus 11n gives me a minus n. Combining those two degree 1 terms, and 36 minus 1 is, of course, plus 35. I think we're doing all right here. Now I'm going to, well, I would subtract n squared from both sides. That'll give me a 2n squared on the left. I would probably then add n to both sides, and it'll give me a minus 3n on the left. And if I subtract 35 from both sides, well, there's no other number term on the left, so I'll end up with minus 35 on the left equals 0. Alright, so that was a bunch of work to get it in standard form. That indeed was the worst of it. Well, in the end, I've got a trinomial of degree 2 in standard form, which I can hopefully factor as a product of two binomials. Alright, if I put 2n and n in the first slots, I think I see it here. 35, well, 7 times 5 is 35. I picked that because if my outer product is minus 10 and my inner product is plus 7n, let me say that again, if my outer product is negative 10n and my inner product is positive 7n, indeed those inner and outer products will add up to a negative 3n. Alright, so convince yourself that I've got the correct factored form there. I'll then branch off into two degree 1 equations with the word or in between them. And of course then n equals minus 7 halves or n equals positive 5. Alright, so we've done 5 or 6 examples of this technique. And again, it is the culmination of Chapter 5, really. The most important use of factoring is to solve equations of higher degree. Alright, we're at about the 28-minute point, so we'll call it a day for this section, and that is all.